Welcome back to Stay Sharp in Digital Engineering, your insider's edge on all things digital in the world of engineering, products, and manufacturing. In this episode, Jonathan Scott and I invited in Shawn Freeman from Vias to help us explore all sides of simulation as it relates to a digital twin. From surrogate modeling to AI's future, we explore how these tools are transforming design and operations. Let's tune in. Hey, welcome back, everybody, to Stay Sharp in Digital Engineering, the podcast where we talk about all things digital related to products from engineering, manufacturing, service, and beyond. I'm one of your hosts, Julianne Grant, and today I am joined by my co-host, Jonathan Scott.
Hello, everybody.
It's good to be back here, Jonathan.
It is.
It is. And today we are continuing our digital twin series. We've had several episodes on digital twins so far. And today's angle is about simulation. Now, we've touched lightly on simulation in several conversations we've had, and referring to scenarios such as, front-ended simulation and those kinds of things. But today we're going to explore much more directly about how digital twins and simulation work together. And to do that, we have a special guest with us today who knows quite a bit about this topic. And I'd like to welcome Shawn Freeman from Vias joining us.
Thank you. Good morning.
Morning, Shawn. So just a little bit about Shawn, for those who don't know him. He has 30 years experience in his career, and he started in vehicle safety and a CAE engineer, consulting for General Motors, Chrysler, Mercedes, Toyota, and also his own employee of Ford Motor Company. He then transitioned over to CAE software development, where he held positions at Altair Engineering, MSC Software, before he joined Dassault Systems. And so in addition to vehicle safety, he has a lot of experience in simulation data and process management, engineering services, custom software development. And so today, Shawn works at Vias, which is a Dassault Systems Platinum partner focused on simulation-driven product development on the 3D Experience platform. So we're really glad to have you here today. You certainly have a background and have some experience in simulation. So let's jump right in, Jonathan.
Yeah, I'm excited about this. And Shawn, thanks again for being here, because I think this topic is one that jumps right to a lot of people's minds. When they think about digital twin, they are thinking about some kind of simulation. So I really want to dig into this. And let me just level set for the audience, because if you've been listening to this series, we talk about a lot of things. Digital twins can mean a lot of things to a lot of people, including electromechanical products, cyber physical products with software and that sort of thing. But for today's conversation, I think we could spend way more than the time we have if we brought software or kept software in the equation. So let's set that aside for a minute. And I want to dig into simulation related to our physical products, right? And talking about just what is it we're doing with simulation on physical products? What can we predict? What do we need to know? What are the components that are useful to make the kinds of digital twins that people are looking for? And, we've done a lot in other episodes setting the stage for different kinds of digital twins. And I think we're focused on the more traditional one here, the case where you've got data about your product and you want to know something about its performance in the future, right? And I think simulation fits right within that. So let's start there. Where do you see simulation technology fitting within digital twins?
Sure. So, if you really want to position traditional CAE within the digital twin, you have to also keep in mind that traditional CAE is typically very long-running simulations.
Right.
And a lot of the simulations are tailored towards a specific use case and a specific configuration of the product. So they're not looking at the entire feasible realm of the product or the product's performance, which is, I think, really what you want in a digital twin. So with the traditional CAE, you're looking at one particular performance criteria. Maybe it's, the crash test or the NVH performance. So in that regard, traditional CAE tends to play more of a supporting role to the digital twin as opposed to being, directly integrated with the digital twin.
Okay. That makes sense, right? I mean, to your point, if you're trying to sort of exercise your digital twin to get some answers about its performance in a certain situation, you're not going to want to sit down and say, okay, let me plug in the situation and then wait a half a day to get your answer. That's kind of what you're talking about, right? The traditional CAE is going to be that kind of thing, and also very focused is what you're saying, maybe on one aspect of performance?
Yep, exactly. So I'm going to stick more with vehicle safety because that's what I used to do. But when you're looking at the performance of a vehicle, right, typically what you're trying to do is understand how the structure behaves, how it's going to absorb the energy, and how it's going to protect the occupant. Now, all of that can be done within a vehicle crash simulation, but the things that you can't get out of that is, or the aerodynamic flow of the vehicle, right? What's the NVH performance of the vehicle going to be? That's a different set of simulations that have to be performed, equally as long running, but each one of those types of tests that you want to perform or virtual tests that you want to perform will require a separate simulation to be done.
Yeah, that's a great point, right? So simulation does not mean like, oh, just tell it the temperature and pressure outside and suddenly you'll know the performance of the car, right? It means, well, certain cases, certain conditions for certain kinds of simulation and prediction, and those might all be discrete, different things, to your point. So you're not necessarily running them all at once and just getting the car's going to do this or the plane's going to do that out of it.
Yep.
And one more thing, you mentioned an acronym I'm not sure the audience knows, NVH.
Yeah, so noise, vibration, and harshness. So that's when you're driving in a car or any kind of vehicle, the vibration and the noise, it's really what gives you the feeling of quality, right? So when you're buying a product or specifically a vehicle, right, you want to have it to be quiet, smooth, no rattles anywhere. And that's really what the NVH simulations are about, is checking that kind of quality of the vehicle. And really, that's an important consumer measure. If we look at something like vehicle safety, it used to be a really big deal to be NCAP 5 stars, and that was a big marketing thing, but also that's a very critical safety. So while you may not, directly interact with the safety systems unless you're actually in an accident, it's always nice that those systems are there and that they're well proven. And simulation really does a lot of the heavy lifting to make that happen.
So I think just by talking through this, right, you're bringing out this point very clearly with the example of an automobile and some form of transportation, that you've got safety, you've got performance, you've got quality, right? Like you said, NVH is sort of that, it's the quantitative version of the qualitative feeling of being in a car.
It gives you the experience.
All these aspects. Yeah. But all these aspects, right? So it's not just one simulation, it's all these different modes that you need to consider. And if they're all long running, okay, that brings me to, so how does that work then? How do we use simulation in the context of a digital twin if we can't just sort of, get answers like that out of these tools?
Yeah. So there's actually a lot of different methods. We're going to focus mainly on what we would call surrogate modeling. So in surrogate modeling, what you'll do is you'll take a complex simulation, or actually a family of complex simulations, and you might perform something like a design of experiments to explore the design space. And what that might mean, I'm going to take a really simple example like a bottle, right? So if you have a bottle of shampoo and Procter & Gamble is going to put the fluid in the bottle, stack it up in many pallets and truck ship it to, let's say, Walmart. If you have that bottle of shampoo, there's lots of design parameters, right? How thickness is the wall going to be? How wide's the base going to be? How narrow is the neck going to be? How tall is the bottle going to be? What material will it be made out of? So you can run a design of experiments over all of those different parameters, knowing that the load from the pallet stacking is going to be X.
And just real quick, Shawn, the design of experiments, right? For those of us that aren't engineers who are listening, the idea you're talking about is you would decide which variables out of all those you mentioned to vary and how, and then combination. And over that, you might choose which ones of those to actually run through a test. Is that what we're talking about with DOE?
That's exactly right. Yep. So you'll pick the parameters that you want to run. Basically, what do I want to study? And some of the parameters might actually be the load, right? Can I stack it 5 pallets high, 7 pallets high? So you'll run that design of experiments, which is really to explore the feasibility, the realm of feasibility for that package design. And then, based on that, you'll have what your inputs were, right? What was the load? What was the wall thickness? What was the material? And your outputs. At what load did the bottle start to crush? Will be one example of a response. And then you can map, just using regular old mathematical equations that you can do in something like Excel, you can actually map those responses back to the inputs and create what we would call a response surface. So that response surface is really just a bunch of equations.
And that's when you said surrogate earlier, that's the kind of thing you're talking about, because that's representative then of what simulation you might want to run, but without having to run all those. Is that the idea?
Yep, exactly. So that response source will be one type of surrogate. There are other types of surrogates that we would do. So for example, going back to crash, we used to do what we would call stick models. So you would build a model of the vehicle using 1D elements instead of the full 3D representation. That would be another form of fast running surrogate. Maybe, some people would do some MATLAB equations, for example, is another form of a surrogate. So there are different forms of surrogates, but they all really serve the same purpose, which is, can I get a quicker run, a quicker response to my inputs to measure the outputs without having to go and wait until tomorrow to see my results?
Yeah, or use an entire data center to do it or something like that.
Exactly. Yep. Exactly.
Okay, well that makes a lot of sense, right? So that's how, I guess at the surface, I know I think of like, oh, simulation is great. It's a key part of digital twins. Of course you need it, but there's this layer beneath, which is, well, yes, you do, but it's actually a series of things that you need. You need the real in-depth analysis to sort of map out the playing field of possibilities, and then to come up with some, I guess I'd call them assumptions, right? That surface map that you mentioned about, well, here's generally how it behaves without actually going through the detailed analysis. And that's what you need for speed. That's what we're getting at, right?
Yep, that's exactly right. And those models have other uses, but we can go into that in more detail in a minute. But yeah, carry on.
Yeah, and one question that I have is, so as I'm envisioning what you're talking about with the surrogates, so I envision this sort of iterative, multiple type surrogates. There must be more than one that gets generated throughout this process, right? Or is the end result just one?
It actually depends what you're trying to do, but most of the time, if I really want to influence design, so in the concept of really, in my view of digital twin, which is influencing design and manufacturing, if you really want to get engaged in that realm, then you have to have more than one, right? Because if I prepare one, it will be the one for the crash, and somebody my co-engineer might prepare one for NVH, and ultimately, you're going to need all of those surrogates together in order to get the total behavior of the product, right? So if I'm a design engineer and I'm looking at a beam, for example, in a car, and the crash guy wants to stiffen that up, but the NVH guy wants to lighten it so that it's not creating noise and vibration problems, you need to be able to see both of those sets of results simultaneously.
Okay, great.
Yeah, that makes sense, right? This is where I think digital twins get so complex, is when you sort of step back and look at them from a business view and to think about some of those business use cases, a lot of times they're holistic. And the holistic view takes a combination of a lot of these scenarios you're talking about, Shawn, right? Where in design, you might have a particular goal or a focus, and it's like, well, we'll compare this against that. We'll optimize this given that constraint. But in digital twin, it starts to get complex when it's like, well, I want to know about all of it. The noise, the performance, the gas mileage, the crash safety, the this, the that, it's all these things together. I want to come back to, I think, the core question for me in this series that we're talking about, and that's about sort of components, right? We talked about in other episodes, like the components of data management and mechanical design and lots of other things that fit into a digital twin and where they fit. Let's talk for a minute, if we could, about the components of simulation. Like, what are the pieces, of simulation writ large, that big body of work and capabilities? What are the components that are relevant to digital twin that people should know about and understand something about?
Well, I'm gonna back up maybe to 30,000 feet and just talk about simulation in general. And at that level, there's really four main components that every simulation would have in common, right? It's the inputs that we already discussed, and the outputs are the results. There's also the model, which is the representation of the thing you're trying to simulate. And sometimes it's the product, right? So if I'm doing that shampoo bottle, it would be the product. Other times it might be things around the product, right? So if I'm looking at the airflow over a wing, for example, I'm doing that to fine tune the wing, but what I'm studying is the airflow. So there's the model, and again, that's the representation of what you're trying to study. And then ultimately, there's going to be some kind of a solver, which is really just taking all those constitutive equations and solving them. So the model will take, but let's keep it simple with a plastic bottle for your shampoo. The model will turn that CAD geometry into a discretized surface or collection of surfaces, right? Along with the connections and the loads and the boundary conditions. And then we'll feed all that into a solver, which basically is going to take that set of equations based on the loads and boundary conditions and properties that you've given it and run all of the calculations to get to the result for you. So those are really the four main components. So your input, your output, your model, your representation of what you're trying to investigate, and then the solver, which does all the number crunching for you.
So you bring up an interesting point there, Shawn, and it's something tangential to what we've talked about in other episodes on digital twin. We've talked some about digital twin and manufacturing, right? And that digital twins are not just of the product, they can be of the manufacturing process. You're bringing another angle, right? Which is sometimes the situation you're trying to solve, the thing you're trying to predict is actually the environment around the product, because that's going to then influence how you design the product. So that's another interesting one that I don't think we've really talked about a lot to date, but I'm glad you brought that one up. That's fascinating.
Yeah, because I'm thinking the same thing. It's sort of like it brings in the behavior-ish part of the product, in terms of how it's responding to the environment. And we've been mostly focused on the physical part. So, we're figuring that you're getting all the data pieces, the model data, relevant information, into the digital twin. So help me understand like how we take, I don't know if this is the right next question for us in this discussion. So Jonathan, put me in my place if you need to. But help me understand, like, we got all these models, we got these surrogates. Now, how does that get into a digital twin, or is it, does it become part of the digital twin model? How does it all come together?
I think it's a great question, Julianne, right? We've got different things, and I'll put it, I think, in context of something I was thinking when Shawn was describing those components, right? That if you've got inputs, outputs, a model, and a solver, is when we say surrogate, Shawn, are we really talking about it's just a different model? It's a different kind of model?
Effectively, it is. And I'm reminded of a movie, I think it's Synchronicity. I can't remember the exact name of it, where, a copy of a copy of a copy. So your CAD geometry is a representation of something in the real world, and your simulation model is a representation of that. And then the surrogate is representation. So yes,
right.
But hopefully you're maintaining as much fidelity as you can. And so yes, to answer that, but if I can go another step further, as I'm talking about kind of this chain of things that are each one leading to the next one, you also need to maintain the pedigree, right? So having a surrogate model and not knowing, where did it come from? And what's the quality of that model and the quality of those results? I think that definitely plays into the digital twin, right? Because part of that whole pedigree and knowing, do I actually have good data? Do I have a good model here that I can trust when I'm making decisions?
So that sounds like something I've, heard all throughout my career in working with simulation, right? And so, my background's mechanical engineering, and I did about this much simulation, enough to be dangerous, and got reminded of that by many people who were experts at simulation. But that point of, simulation is only as good as the inputs and knowing the limitations of what you're doing. And I think that's what you're pointing out, right, Shawn, that, you can have a surrogate, you can have a lower order, a lower fidelity model, and that could be very useful as long as you know the limitations and you understand how far to take it or not take it. And that's kind of what you're getting at with pedigree, right, is knowing, where did this come from? What is it good for? What is it not good for?
Exactly. You need to know those assumptions that the guy upstream made. And a lot of that is, how do I manage the data? How do I manage the transparency? How do I manage the history? And if someone discovered a problem anywhere in that workflow, right, from design all the way down to using my surrogate to make a decision, how do I find that? How do I trace it? And then what steps can I take to correct it? Right? If I'm doing this just on a file system and it's a bunch of siloed different teams, it becomes a pretty big challenge.
Yeah, well, that makes sense, right? And I think this idea of using surrogates in digital twins if you want fast answers, or thinking about different use cases for simulation maybe than people, I guess, in the widespread world have used simulation for in the past, is going to raise these questions about, like you said, how can I trace back to what I did and make sure that it's right? Or if there's a problem, trace forward to correct it, so that, a digital twin that somebody uses to make business decisions on is always the most up-to-date, the most accurate, the best it can be. And I think your point is, you really have to think about that process. You can't just oh yeah, here's a surrogate, go nuts, good luck.
Exactly. Yep.
Okay.
Exactly.
Well, right. And like, where does all this information get stored so it can actually be referred to back if you want to look back at historical, surrogates that did some level of testing to solve a problem that maybe is recurring? Where does all this stuff live?
Sorry.
It's a basic question, My head is like, okay, where do I put all this stuff?
I'll give you a funny story without actually naming the customer. So I went to visit a customer one time, and they were talking about all of their surrogates and their CAE models and how robust a process they had for running it, tracking it, traceability, and data management. And they brought up on the screen this giant, beautiful folder structure that they had, and all the tools they had built around the folder structure. And they kept going farther and farther down, and they got down to, let's say, the fifth or sixth level. And I said, okay, well, what's below that? We don't know. So they clicked and opened it up, and it was absolute chaos. So they had this beautiful process with all these folders, and all the engineers were doing where they were just going down to the very node, and then they would do whatever they wanted. It was the Wild West all over again. Like, well, you almost had it. You were close.
The junk folder. It's like the junk drawer.
That's right.
Yeah.
That's right.
Yeah.
What's in there? Who knows? I don't know. Don't ask. Yeah. But that's a great point that you're bringing up, Shawn. That example, right, paints the problem clearly, which is if you really want pedigree and traceability and you want to trust these digital twins, you have to have control over that process, over that data, all of those things. And I think, this isn't necessarily what everybody thinks of first when they think of PLM, but I think this is an important aspect, right? That you need to think about the control over the data that's feeding the simulation, that's feeding the prediction, that is maybe why you started to build a digital twin in the first place.
Absolutely. And honestly, I think, I don't want to turn this into a PLM pitch, but, if you think about it, putting it in the PLM not only solves the vast majority of those kind of chaotic problems, it also breaks down silos. And, in all my time in engineering, the silos are still there, right? So the crash guys are separate from the NVH guys, or separate from the vehicle dynamics guys. And at the middle of all that is you've got the poor designer who has to try to somehow communicate and interact with these different engineers who sometimes, engineers can sometimes be a little bit difficult to work with. And I think the PLM can actually help break down those silos, right? As we have a digital twin and we have the surrogates in there, and we're pushing more of that capability to the designer to say, well, can I take a quick look at the NVH? Can I take a quick look at the crash? And, really the nexus is happening with the designer, not necessarily in those individual silos. And in order to make that happen, you have to have a system, right? You can't just say, well, my folder, your folder, and we're going to hope the guy figures it out.
Yeah, no, that makes perfect sense, right? The platform can become the collaboration tool that we need it to be, right? And that's what you're getting at. I want to go back to the surrogate topic for a minute, because it raises a question for me, Shawn, about other terms that I hear in the industry and things, again, I know this much about. I'm hoping you can enlighten us a little more. And that is these lower order models. And maybe that's not even the right term for it. I should just stick with surrogate. But I hear and I see things in the MBSE world about running simulations inside of MBSE, and about how MBSE tools can reach out to these, what I would call surrogates, right? Simplified models of some physical behavior. And it reminds me of this term I've heard, FMI and FMU, functional mockup. Can you tell us a little bit about that, and how does that fit into this picture we're talking about?
Yeah. So actually some tools will actually, so those are standards that I couldn't tell you which standard which body they're coming from, but those are standards. And if you look at tools like, I don't know if it's safe to mention one, but I'll mention one. Simpact, for example, has the ability to export, and it does have a real-time solver, so it has the ability to export the FMU that you can actually import into MBSE tools, and then it can do a real-time simulation of that particular model with those little cases that you've built. So that is a way to kind of encapsulate the simulation and then make it available to other tools. It could be MBSE, but it could be actually other CAE tools as well, right? So
that to me helps connect the dots some, right? Because as we sort of roam through all the different technologies and capabilities and how they support digital twin, that was a connection that made sense to me, right? That MBSE as a systems engineering tool when you're talking about a complex system, like an aircraft, a car, or whatever, it really is made up of a bunch of systems. So if you can analyze those with their own physics, their own things, like we were talking about earlier in the conversation, all the different physics or studies you might need to do. But if that system analysis tool can bring those together and the surrogates, the simplified versions, then you can start to get that holistic view of like, okay, well, if it flies this fast, then I'm going to use the Aero model to determine how much fuel it's going to use. Well, if I know how much fuel it's going to use, I can put that into another model that'll, and you start to connect the dots. So that's what I want to make sure I understood is it sounds like FMI, and that standard is giving us some ability to connect these things in a simplified way to get to what we want to get to. Am I catching it right?
Yep, absolutely. And it does have some advantages over, like the response service that I mentioned earlier, where, if you look at a response service, you're really getting the inputs and the outputs, but you're not getting any of the field data inside of the model, right? So if I want to know the stress at a particular point, I'm not going to get that from the response service, whereas, the FMU and the FMI should be able to provide that more in-depth information about the results in the simulation. And I'm going to segue a little bit, that's actually where AI can come in as well, right? So
okay.
The AI starts to build up, a surrogate model. Those are different from the response service in the sense that they can actually create the measures inside the field data as possible with the AI. It's still very new, and a lot of companies are working on it, but I think that could very well be the next evolution of the fast running models, and maybe potentially even replace the FMI and FMU eventually.
Okay, so it's and I'm definitely at the edge of what I understand, so I'm going to ask more questions to make sure I get it. You're talking about these the surrogate models. There are actually a bunch of different modes of surrogates we could have, and AI is potentially a new mode of a surrogate that could give us richer data. And how does that work? And I mean, is there any of that you can sort of explain? It's obviously it's different, but how's it different and why?
Yeah, and I'm not an expert either, but the simplest way that I understand it is, and I'm going to make the distinction with the response service, right? If you've got inputs and outputs, you're literally just doing polynomial equations that connect the in and the out, and that's
okay.
it. And those, they're 100% meant to transform input to output, but what happens inside the box may not actually be representative of what's happening inside of the physical product or inside of your simulation. AI is taking a different approach where the inputs and the outputs, but all of the data is actually part of the solution of the machine learning model, right? So it's not saying I'm going to just do a polynomial between here and there. I'm actually going to try to understand what's going on inside of the model. What is the stress at that location, right? But then with that kind of data, what it's actually trying to do is create, an accurate representation of the inner workings of the simulation as opposed to just the endpoints. And with that, now I can actually go back with my AI model and say, okay, well, there was one question I wanted to ask, but my response service can't answer it because I didn't think to ask it before I built that response service, right? But with the AI, okay, because I have that internal view of the data, I can actually go and ask more questions and get more answers than I probably would get with a response service. So
basically, our surrogates can get richer and richer. They're still approximations, but we could get more answers out of them.
Yeah. I mean, I'm an engineer, not a mathematician, but my delusional thought is if you get an AI model down to the same fidelity, you'll eventually get back your finite element equations. Right. I mean, eventually it's going to reverse engineer the finite element solver.
That's hilarious. Actually, I hadn't thought about that, but it makes perfect sense, right? Like, what is it doing? Well, it's goal-seeking on the thing that it came from originally. So, yeah, all right.
I'm sure you're going to get lots of comments about that from all the mathematicians. But.
Well, welcome the comments for sure. Yeah. So one of the things I'm in my mind is when I think of simulation, I think that its outputs will then end up in a digital twin somehow. But is at this point with the popularity and the drive for digital transformation, are digital twins now deriving more simulation? Is it coming from the other direction, or is it always just sort of the solving and then eventually some data gets represented in a twin?
I think we're actually at the inflection point now where that is starting to happen. So we did project, and I want to discuss a few years ago, we did a project with another major OEM, and that's exactly what they wanted, right? They wanted to go into multi-domain stuff. These were going to be the response service approach, but go into multiple domains, drive all these response service generations so that they could have the designer sit there and let's say, intelligently design a product without going into an infeasible space, whether it's NVH or crash or anything else. And in those kind of scenarios where you have companies saying, hey, this is what I want to do. I want to enable designers, or even, we do simulations of the line speed in manufacturing, right? Or I want to enable them, that as well. In those cases where companies are starting to say, this is what I want to enable, they are switching, kind of switching it up and saying, we're going to drive the need for simulation. So instead of you studying one particular test, we want you to explore the entire realm. And then we're going to use that data to drive more upstream decisions. So yeah, I think we're actually at the point where a lot of it, because of data management and just the scale of everything, it's actually possible now to flip that equation around and say, yeah, we're gonna drive the generation of the surrogates for other purposes, not the other way around. Not just have a happy outcome of our simulations that we can get a surrogate. The other way around to say, hey, surrogate is the purpose. Right?
That's interesting, right? And it goes back to something you said earlier on. I didn't dig into, probably should have. We've talked a lot about the purpose of a digital twin on the podcast and on the series, that you have to have that purpose in mind. And you mentioned, a lot of the purpose we see is about going back to design. In my mind, a lot of the purpose has been about operation and use, right? And what people want to do with the product there. But you're bringing up a really important point that some of the capabilities we're seeing in digital twins and the reduction of cost of compute and data and all that means we can start to see some new use cases. And that's what you're talking about there with that inflection point, right? People are changing how they're using this.
Exactly. And I did skip over one thing, which I'll circle back to on that comment. There is actually the operational aspect of this work as well, which has kind of been there for a long time in A&D. It's pretty common for the manufacturers, so Boeing and Airbus, for example, to actually keep some form of a surrogate model. And when, let's say, Delta Airlines has something, maybe just maneuvering on the runway, something taps the wing or whatever, they will call up the manufacturer and say, hey, this is what we had happen. Here's the conditions. And they can run it through that surrogate within the realms of safety and confidence and come back and tell the airline, okay, yeah, it's safe to fly. That's not going to cause any damage. Or you know what? That's in an area where our models are saying it could be in the yellow zone. Maybe you better ground it and do an actual repair and inspection.
That's interesting, right? That's the use case that I sort of have in mind with a lot of my questions today, is that operational one of, hey, this happened. What does it mean? What can we do? Or how can it perform some future thing? And I think all of these are valid and important use cases, but that was a great one you gave about sort of the operational response and why you need to not say, oh, hold please, we'll get back with you in a day to answer that question. We need a responsive digital twin to answer those kinds of questions.
Right? Yeah, they can't sit there waiting for a day. Millions of dollars are going out the window as long as that plane is grounded, right?
Right. So I've got another question, but I'm going to guess, Julianne, you might tell me there's no time. Is there time to sneak one more in?
We can sneak one more in, but then we'll need to wrap.
Okay.
I'm sure it'll be a good one. So.
Okay, so it's really, I guess it's more operationally about digital twins themselves. And I always think, when people talk about IoT and IIoT and that real world data, that, okay, that sounds really important to digital twins. If you want to know how this one's going to behave compared with that one, of course, it's important to know what situations were they in and what sensor data do you get. How does that fit with the simulation components you talked to us about earlier, Shawn, when you mentioned, input, output, the model and the solver and other pieces? Like, how do we use the real world data to come back and inform what we do with simulation and digital twins?
Yeah, it's a great question, and I'm gonna answer it, and I'm gonna segue for just one quick second. So the sensor data, and it could be from the real world, it could be from a physical test, right, which is still the real world, but not operationally speaking, right? So that sensor data is actually used to inform how we would calibrate or correlate the models back to the real world. So, that sensor data becomes input. And when we're running the long-running simulations, we're actually looking at virtualized sensors, the same exact sensors, but virtualized in the model. And we're comparing those against the ones that we measured in the real world. And that is really used to make sure that our model is giving us, again, within the realm of our assumptions, is giving us the predictive capability that we expect. So you don't want to just build a model and not have any kind of calibration or correlation and then start trusting that it's actually going to give you something meaningful, because that's absolutely not going to happen, right? So that sensor data is really used to drive the quality of the model. It can also flip around, which is my segue. One thing that we've learned over the years is that simulation can drive testing in the sense that we can do a lot smarter. When I started out, we were, Crash, we were just throwing everything at the wall. Money was no object, and we would do a simulation afterward. And what we kind of flipped that around and said, well, let's run as many simulations as we can and fine tune on the problem areas, right? Let's try to understand where we're having the most difficulty with this product. And that's what we're going to physically test. We're not going to physically test the whole world. We're going to only physically test the areas where we know we're having a problem and we need more information in order to further verify and vet our models. And by doing that, you can greatly reduce the cost that you're spending on physical testing by saying, let's look at the simulation model to actually drive what we do in tests. So it becomes very symbiotic, right? Where the physical test is improving the quality of the simulation, and the simulation is telling us what tests we need to run in order to make sure we're getting the right kind of data at the right price point.
That makes perfect sense, right? I mean, you're optimizing, and it goes back to your design point. You're optimizing your tests so that you get better answers for design instead of just testing everything and hoping to find the needle in the haystack. Oh, there's where the problem is.
Yep.
Yeah.
Exactly.
Great.
Okay, Julianne,
Yes,
I'll stop.
yes.
No, that was very helpful though, Shawn.
It was very good. This has been a fantastic conversation, but it is time that we're going to have to do a wrap up. So, Jonathan, do you have some thoughts on what we've heard today?
A lot. Yeah. No.
This has been great, Shawn, really.
It has. It has. This has been fantastic, Shawn. Here are the things that I heard, and I'm looking for you two to chime in with what I missed. But I think we started with a very important point, which is the simulation that many people may traditionally think of, plug in some information, run a model through a solver, get some outputs, is not necessarily what people are going to use in a digital twin, or at least not a responsive digital twin that a lot of people think about when they think, oh, I want to query my digital twin and get some answers, because of the long-running nature. But it's key to the process, and that process involves a term that you brought to us today, Shawn, I think is very important, and that's surrogates, surrogate models, right? And the idea that your really detailed simulations can inform and create your surrogates, and those can take different forms, whether they be things like functional mock-ups, or they might be AI generated or other modes. But the idea is they're simplified versions of our detailed model, but that we can run quickly, we can get answers from. But if we're going to use those, we have to be careful that we make sure they maintain their pedigree, that we know where they came from, we understand their limitations, how they can and shouldn't be used. So we have to put all that together, and this comes back to kind of a PLM-ish problem, right? Without getting into that topic, that wasn't the intent. I think we did. And it's pointing out that all of this has to be connected data. So your digital twin can't be just discrete little pieces of information. It has to be connected and maintain that pedigree. I think that brought up another interesting point on the use case you were focused on today, Shawn, when you told us, a lot of this is focused in design today, digital twins for design. But what it's doing is it's breaking down the walls and the silos across organizations and saying, if you want to understand your product performance, and everybody who's involved in its design should, you need access to this. Everybody needs to have a look at that digital twin. And then the last thing I took away is that through all of this, real world data is important. It's always been important in simulation to calibrate and correlate your simulations against the real world. But that's even magnified as we get into digital twins and you say, well, you want to know how that one performs compared with that one? Well, they've each had different lives. They've each had different circumstances that IoT and real world data, and even IIoT, maybe from manufacturing and its processes of how it came to be, all of that real world data can inform the simulations that we run against the product to know how it's going to behave in the future. So in a nutshell, that's what I heard, but I am sure I missed some things. Julianne, Shawn, what did I miss?
I don't think you missed anything, actually. That's quite amazing. Nice summary. Yeah.
It is a good summary. The only thing I would add is just kind of where it's all going, right? So, historically simulation kind of drove design, but now there's this inverse inflection happening, as Shawn indicated, that, now that they're starting at the product and trying to more look at holistically, how to fix key areas. So there's, it's kind of coming from the other direction, from the twin to drive simulations. And then we just, you lightly touched on AI, Shawn, but I think, when you think about how AI is so good at looking at all the data that's there and then extracting information and making good use out of it. And it can just only imagine it's going to accelerate the pace of which, simulations happen. And then, how quickly people can solve these tough problems, especially when there's, like you said, behavioral issues in products that really affect a user's experience. And certainly, flying a plane is one of those things. Nobody wants to hear banging and clicking and noises there. Certainly, and I hear them in my car, so we don't hear them there either. But when you think about what the capabilities of AI can really do to accelerate and make this information more available and quicker to see trends that we might not be able to see, I think that's going to be very interesting as we go forward here on this wave of AI, if you will. Right?
Yeah, I think that one is a good point. I did miss Julianne. You're right. It's going to be very interesting how that fits into this whole picture.
Yes.
Well, I will say, before I let you wrap up, Julianne, this has been great, Shawn. It's been a fantastic conversation, very enlightening about the elements of simulation and how they fit into the digital twin. Because I knew there was a connection, obviously, right? We've all been in this space long enough to know there's a connection. But to really understand it, this was very helpful.
Yes. Thank you. And thank you for having me on. I appreciate it.
Yes, thanks so much on it. I agree with Jonathan. It's been a great conversation. So as always, though, there are more angles to all of these topics and digital twin and digital transformation. So if anyone has any questions for Shawn, want to make a comment, please make a comment on our post or send us an email at podcast@razorleaf.com. We're so glad you joined us today. And to our audience, we're glad you're listening in today. Shawn, we'd like to keep the door open to have you come back. I think there's a lot of runway here to talk about simulation as we go forward. We'd love to have you back.
Thank you. Thank you.
Okay. Well, with that, everybody, we're going to close out today's episode. And until next time, stay sharp.
Thanks, everybody.
Thank you.
Bye.
Thanks for being here and listening to this episode of Stay Sharp with Razor Leaf. We appreciate you. If you like this podcast, please be sure to hit the like button and subscribe to our podcast on your favorite podcast platform, or check us out on YouTube. If you have any questions, please leave us a comment on our post or send us an email at podcast@razorleaf.com. Until next time, everybody, stay sharp.